Now let us define random variables. Let us see why we need random variables. What are the applications and so on. So in many areas, the outcome of an experiment, like in physics and engineering, medicine, are often assigned to quantities, and they are random. In many applications, the outcome of experiments are themselves numbers. They could be locations. So the numeric values observed or measured are random. So a random variable can only take on numerical values. So you have to remember, a random variable is not a numerical value, but can take a numerical value. So we want to define these properly in this chapter. So we will give a very precise definition in this chapter, which is a random variable is a function, is not a number. And this function maps the sample space into the set of real numbers. Suppose that this is your L, and you have different possible outcomes. This could be like C. This could be another possible outcome. So let's say if you roll a dice, this L has 6 members. Now a random variable is a function, is like a machine which takes one of these outputs. So this is x of C. So it's a machine. So this C is the output of your experiment, and x of C, which is the output of the function, is the value that your random variable takes on. So the machine here, the function, this is a random variable. Okay, this is the output of the experiment, and this is the value that the random variable takes on. I remind you that a random variable is not a number, and the random variable is not random, because random variable is the machine. What is random is the output of your experiment, not the mapping. So let X denote a random variable that is the sum of two fair dice. So what's going to happen is that the possible values that X can take is the smallest value is 2, because if I get in the first experiment of in the first dice, I could get minimum value of 1. The second one I get 1. So the probability of getting x equal 2 is 1 over 62, because if I assume that these two dices, they are independent, so this one is 1 over 6, this one over 6, so I get 1 over 32. Now, if you get the next number as outcome of the sum of the two dices, the two possible cases, if you want to have x equal 3, one case is that you get 1, 2, or 2, 1. So you have two possible outcomes. The total possible outcomes is 36. You get 2 over 36. This is assuming that your dices are both fair and independent of each other. If you want x to be 4, then you have 3 possible cases: 1, 3, 2, 2, and 3, 1. So probabilities and so on. So you can calculate the probability of x taking different possible values from 2 to 12. So here I plotted the probability of x taking different values of k. So x taking these different values of k, and k could be either 0. So this is one possible value. Probability is 0, because neither of the dices give you 0. Here you get also 0 probability. So the smallest value here is 2, 3, 4, 5, 6, 7, 8, 9, etc. And the probability is like that. So it's 1 over 30, this should be 1 over 36, and so on. So the randomness lies in that if you repeat the experiment, you don't know the result. Okay? The randomness is not in the mapping. So here x, the random variable, is x of, let's say, So you have two dices, xc1 and xc2, and is equal to the xc1 plus xc2. This is 1 to 6, this is 1 to 6, so this guy could be from 2 to 12. So this mapping, this summation, so is not random. What is random is the values that the dices can produce. So, so this name of saying x is a random variable is confusing because this is not random, but it allows us to study random phenomena. So suppose that L is a sample space with a defined probability measure, and a random variable is a function which maps L into a subset of real numbers. So we need to, and so these are two properties we need. The third property is that the probability should be meaningful for that. So in this course, we use generally bold letters for random variables, and we refer to them random variables. We will define what mathematical definition of random variables, so we'll do it in a couple of minutes. And hereafter, so bold letters are reserved for random variables, and random variables are functions. And the small lowercase, which are not bold, they denote real numbers. So this is one real number, this is another real number, and so on. So these are real valued variables. And for any member of your sample space, x of c is a real number, because this is c is the output of your experiment from L, goes to your machine. X is your function, and the output is x of c. So it's kind of a random variable is just a function. So what is the relationship between a random variable and events? So we have to establish these. We will learn about it. So the mathematical notion of x equal x, here, this is a definition. This is not equality, okay? We say that this is a function equal x. So this is an abbreviated notation that we use as engineers or as scientists. So these, hereafter, this is a set, subset of L, which includes all members of L such that x of c is equal to x. Okay? So suppose that c itself is a real number, and suppose that x of c be equal to c2, so you will have this function, okay? So if I say x equal 2, it means that this is a set of all possible, your L is real numbers, all c such that x of c is equal to. And this means that c to the power of 2 is equal to, so this set includes two numbers, plus the square root of 2 and minus the square root of 2. So in other words, so you will get here value 2, and then you will look at your set L. This line is your set L, okay? You look what are the solutions of these which will satisfy these equality. Okay, so you have two members. So this is a set including a square root of 2 and minus a square root of 2. So this is a new notation. So similarly, x is smaller than or x is not an inequality. It stands for all members of L such that x of c is smaller than x. For instance, if x of c is equal to x2, and if I say x is smaller than or equal to, let's say 1, here I put 1, and then I draw a line and see what are the members on this L, okay, which satisfy these ones. So all these points are below this line, okay, so that means that this area, okay, which is equal to the set of numbers, all numbers c between -1 and 1. and 1. So all xi such that these one. So this becomes an interval of numbers between -1 and 1. So in this case, remember that this is an event because this is a subset of L, okay? So remember that this is a subset of L and this is also a subset of L. So these and these are events and they are a subset of L. For instance, in our experiment, if I say x smaller than or equal 3 for the dice experiment, what are the possible phases of dices which will produce less than or equal 3 as sum? So if I get 1 and 1, I get less than 3. If I get 1 and 2, I get less than or equal 3. Or if I get 2 and 1, I get less than or equal 3. So this is the subset of L which satisfy x of xi is smaller than or equal 3. So this is an abbreviated notation, so we have to remember. So remember, this is a member of your sigma algebra. It is an event and is a subset of L. X of x equal x is a set, is not an inequality. Equality, this is not inequality, they are events. Okay, and similarly, if I say x is smaller than or equal x, is an event.